The indeterminate forms. At the end of this lesson, you should be able to evaluate limits of rational functions that initially are indeterminate in form, either of the 0 divided by 0 or infinity over infinity by applying L'Hopital's rule. Let us first be acquainted with the kinds of indeterminate forms that we can possibly encounter. We have the primary forms, the 0 divided by 0, or the infinity divided by infinity form, or the secondary forms, the 0 times infinity, the infinity minus infinity, or the power forms 0 raised to 0, infinity raised to 0, or 1 raised to infinity. Recall that when we were evaluating limits of rational functions and we come up with 0 divided by 0 or infinity divided by infinity after first investigation of the limits, what we did was to simplify the fraction into its lowest terms. In the case of 0 divided by 0, or in the case of infinity divided by infinity, what we did was to divide the terms of the fraction by the highest degree factor of x. This time, when we encounter a 0 over 0 or an infinity over infinity, as a result of initially investigating the limit of a fraction, we will be applying L'Hopital's rule. L'Hopital's rule simply states that if the limit of a ratio f of x divided by g of x as x approaches a initially would result to a 0 divided by 0 or infinity over infinity as we evaluate the limit as x approaches a, then we can indirectly evaluate the limit of this expression using L'Hopital's rule, where the limit of f of x divided by g of x as x approaches a would be equal to the limit of f prime of x divided by g prime of x as x approaches a, provided that this limit exists. So the steps in applying L'Hopital's rule would be as follows. First is to check what the limit of f of x divided by g of x would be as x approaches a, on whether this would result to an indeterminate form 0 divided by 0 or infinity divided by infinity. If you end up with these results, then what you do is you differentiate f of x and g of x separately, and then determine the limit of f prime of x divided by g prime of x as x approaches a. If there is a limit to this ratio, then that would also be the limit of f of x divided by g of x as x approaches a. Okay, let us have some examples illustrating the use of L'Hopital's rule. And for our first example, we will evaluate the limit of sine 2x divided by 2x as x approaches 0. If we will investigate initially what the limit of this expression is as x approaches 0, this will lead us to sine of 2 times 0 divided by 2 times 0, or 0 divided by 0. Applying L'Hopital's rule, what we do first is to differentiate the numerator sine of 2x and divide it by the derivative of the denominator 2x before evaluating the limit as x approaches 0. Hence, we will have, for the derivative of sine 2x, cosine of 2x times 2. I hope by this time you're able to follow how we come up with this expression. As to the derivative of the denominator 2x, we will have just a 2. Okay, simplifying now this ratio of cosine 2x times 2 divided by 2, we will just have a cosine of 2x. So using now cosine of 2x, we evaluate the limit as x approaches 0. This now will lead us to cosine of 2 times 0, or simply cosine of 0, which is equal to 1. Since the limit of this expression here exists, then by L'Hopital's rule, that will also be the limit of the original expression, sine of 2x divided by 2x as x approaches 0. Now, applying the same rule to evaluate the limit of x squared divided by e to the x as x approaches positive infinity. Again, the initial investigation of the limit of the ratio as x approaches positive infinity would lead us to an infinity divided by infinity form. Okay, again, we encounter an indeterminate form, one of the primary forms. So when we apply L'Hopital's rule, again, we need to differentiate the numerator x squared and the denominator e to the x before evaluating the limit of the resulting fraction as x approaches positive infinity. As to the derivative of x squared, we will just have a 2x. And for the derivative of e to the x, we have e to the x. So having now the ratio 2x divided by e to the x, we evaluate the limit as x approaches positive infinity. And when x increases without bound, the product 2x likewise would be increasing without bound. As to the exponential function e to the x, as the exponent increases without bound, the expression e to the x also will be increasing without bound. So the result of applying L'Hopital's rule would still be an indeterminate form, infinity divided by infinity. And as such, because this is again an indeterminate form of the primary, then we can apply L'Hopital's rule to this expression and hope that the resulting limit will now be finite. So the second application of L'Hopital's rule would lead us to having limit of the derivative of 2x divided by the derivative of e to the x as x approaches positive infinity. And differentiating 2x, we will just have a 2, and the derivative of e to the x is e to the x. So using now the ratio of 2 divided by e to the x, we evaluate the limit as x approaches positive infinity, leading us to a ratio where the numerator approaches 2 and the denominator increases without bound. So a constant divided by an expression that increases without bound would be approaching 0. Therefore now, we conclude that this expression here, okay, or the limit of 2x divided by e to the x as x approaches positive infinity would be 0 by L'Hopital's rule. Now, whatever is the limit of this expression would also be the limit of the original expression. So that at this point, we conclude that the limit of x squared divided by e to the x as x approaches positive infinity would be equal to 0. In summary, whenever the limit of f of x divided by g of x as x approaches a would result to an indeterminate form either of the 0 divided by 0 or the infinity over infinity form, then the limit of this expression can be evaluated indirectly using L'Hopital's rule, where the limit of f of x divided by g of x as x approaches a would be equal to the limit of f prime of x divided by g prime of x as x approaches a, whenever this limit exists. So it means that if we have a limit to this expression, that will also be equal to the limit of the original expression. Okay, so that is all for this lesson. I hope to see you in the next lesson.